the last couple of lectures were quite technical, right? And so we introduced concepts from stochastic processes, the Landauer equation, the master equation, the different ways to describe the time evolution of stochastic processes. And then the last lecture was pretty tough. Yeah, so the last lecture we introduced field theory description of these processes, and probably many of you who didn't hear that before were had quite a hard time. The good news is that we don't use that for now. We'll use it later in the lecture, but for today, we won't use that. And actually, you'll be pretty fine with school mathematics for today's lecture. Yeah. So now that we've covered the technical part, the methodological part, let's go into some physics and try to understand how actually order emerges in complex systems and in non-equilibrium systems. Yeah, and let me share the screen. There we go. Okay. Here we go. Now you can see my very sophisticated slides. Yeah, and so what do we mean by order, actually? What do we actually want to understand when we talk about order? Yeah, so this lecture, so there are different kinds of order. And this lecture, I'll be talking about polar order. Polar order is order of direction. Yeah, so which direction are you going? Which directions are polymers pointing? Which directions are spins pointing? Which directions are fish swimming, and so on. Now that's polar order. And here you can see two examples of polar order. Now, on the left-hand side, so I took a picture from North Korea, assuming that nobody from North Korea is joining us, and I'm actually not offending anybody. Now, so this is a picture from North Korea, and you can very clearly see polar order in these soldiers and in the faces of these soldiers. Now, is that the job of a physicist to understand that? Yeah, probably not. Yeah, probably this polar order in this picture on the left-hand side has a very simple origin. Yeah, and this very simple origin is that somebody is probably sitting there, some president or so, yeah, sitting there on the left-hand side, and somebody is telling them to look at this direction. Yeah, and so this is not what we want to understand as physicists. Yeah, that's pretty, we kind of know why they're looking in that direction. You know, if the TV camera would zoom out, we'll probably see somebody important sitting there. So that's not what we mean, and that's the reason it's not self-organized. There's somebody who tells these soldiers where to look, and now compare that to the picture on the right-hand side. That's also an example of polar order. There's also an example of a flock, like a bird flock, and in this bird flock, birds fly in a certain direction. And as they don't fly in random direction, but in somehow aligned directions, you can see these bird flocks in the sky that form these patterns and structures on the sky. So here, you don't have a super bird sitting somewhere and telling these birds where to fly. Now, that wouldn't, even if such a thing existed, it would probably not work, because the bird here on the left-hand side wouldn't have any chance to communicate with the bird on the right-hand side while they're flying. Now, so that wouldn't work anyway. So here, these birds somehow form these structures by local interactions, by short-range interactions. They communicate on very short scales, and this gives rise to order on much larger scales, on the scale of this entire flock here. So we're now also interested in how such order can arise, how long-range order, very large scale, can arise from interactions that happen on a very small scale. So here these birds interact on distances of 1 meter or so, but the order has a scale of hundreds of meters. So how is this scale bridged? And although we'll be talking about non-equilibrium systems in this lecture, it's very often good to take a look at how order actually arises in equilibrium systems. And as you probably know, many people from biophysics, theoretical biophysics, for example, epidemiology, and so they have a background in statistical physics or condensed matter physics. And the reason why they're pretty good in understanding apparently completely unrelated systems to physical systems is that these physical systems that can be in terminal equilibrium actually give us some intuition about how order arises. Now, so let's start with a very simple equilibrium example. Now, so probably most of you have heard of the Ising model. It's a very simple model for a ferromagnet. And in this Ising model, you have a Hamiltonian, so energy. And in this energy, you just say, okay, the neighbor, you have a sum over all neighbors of spins, pairs of neighboring spins. And you minimize the energy if these neighbors are aligned in the same direction. So now the energy favors alignment of the spin in the same direction. But if you write down the partition function, then you will see there's not only energy, but there are also other stuff that's important. For example, the temperature. So how and under which conditions do these spins here that want to align in the same direction in the Ising model, when are they actually capable of aligning in the same direction? And there's a very famous argument that was brought forward by Pio, and this argument goes roughly as follows. So suppose you have a completely ordered state where all these spins go in the same direction. Let's say they all point up. Now, if I flip some of these spins, is that favorable or non-favorable? And in equilibrium systems, favorable means that we lower the free energy. So in this Ising model, let's look at one dimension. We can flip a few spins, like a little block of size L, and calculate what is the change in free energy. This change in free energy, delta F, is given by a component that arises from a change in energy and a component that arises from a change in entropy. That's just thermodynamics. This change in energy somehow encodes these interactions. This change in entropy has the temperature as a prefactor, and this gives us the contribution of the noise. Now, already by this formula, you can see that there's a competition between these two forces. So the interactions that try to minimize the entropy and the fluctuations that try to maximize the second term. So we can just write that down. So if you look at such a domain here, then we'll see that in one dimension, we have two boundaries if each gives 2 times this factor here. And so that's 4 times J minus KBT. And then that's the Boltzmann entropy. How many times can we fit such a block into a system of size n? And then that's just the Boltzmann entropy. So when you can just count, this block would fit exactly n minus L times. So we have these two contributions. And now we go to the thermodynamic limit. Yeah, that means we set n, the system size, to infinity. And in this thermodynamic limit, the second term will always be larger than the first term. Yeah, the entropy contribution will always be larger than the energy contribution. Yeah, and this means that this is always smaller than 0. Yeah, and this is probably a result that you already know, that there's no long-range order in the 1D Ising model for finite temperatures. Yeah, so only at temperature exactly equals 0, you can have alignment of these spins. So what this says here is, so these spins still want to align. Yeah, and you can ask this alignment information about these spins. How far can this travel through the system until the temperature destroys the information? Now this tells you it will never make it through the entire system, yeah, and you will never be able to transport the alignment information of spins from one end of the system to the other end of the system. Now, this is for one spatial dimension, yeah, and in one spatial dimension, every spin only has two neighbors. So if one neighbor changes something, that will always have a strong effect. Yeah? So that will always, these spins are always subject to a lot of modes. The more neighbors you have, yeah, the less important are these fluctuations. Yeah? If you have, for example, in the 2D Ising system, you have 4 neighbors or 8 neighbors, depending how you define it. Yeah? You know that you already, from your statistical physics lecture, you know that you can get order. You get a phase transition from a disordered state to an ordered state. That is, you can see here at the top, that's the ordered state, where all spins are aligned in the same way. And if you raise the temperature, there will be a critical point where, so to say, these both terms from the free energy have roughly equal strength. And if you further raise the temperature, you will see that the system is completely disordered. Yeah. Take home message here is, and of course, if you go to higher systems, then it's easier. Then this same result of the phase transitions will be reinforced, will become as spins are able to average over more and more neighbors. Yeah. So the take home message here is that we have this competition between the transport of interaction information through the system and the noise. Yeah, and the balance between these two will decide if you can have long range order in such a system. And although this is an example from equilibrium, yeah, so this is actually a very powerful thing to keep in the back of your head. Now that you can get order if the interactions, so to say, are stronger than several the sources that lead to perturbations or that lead to noise. Yeah. So here we had a very simple time because we have the free energy. We know where the system is evolving to. In non-equilibrium systems, we don't have this free energy. Yeah? We don't know what is being optimized. And for the rest of the lecture, I will show you how we can transport this argument by Peierls to non-equilibrium systems. So in the first step, I want to stay in equilibrium, but I want to take a dynamic perspective. Yeah? And this dynamic perspective is encoded, so we'll take a dynamic perspective on an equilibrium system. And this equilibrium system is defined on the right-hand side. Yeah, and there's an anecdote actually by one of the people in the field, John Toner. And the anecdote he used to describe this system is that suppose you are in a conference, or you are in the entrance hall after work in your institute, and you are around with a couple of people, and now you stand next to each other and you decide where to go for dinner. And now you all have different opinions on what you decide what to do. How you decide what to do is you all point in a random direction. And then you change the direction you're pointing at depending on what your neighbors are doing. Yeah, you stay where you are, but you point to the directions that your neighbors are pointing at. Yeah, and this is depicted here. We have these points here. That's you deciding where to go for dinner. And so here we have the point in the center, and this point in the center has an interaction radius. Yeah, and within this radius are not, this point looks around and averages its new direction over whatever it finds in this vicinity, in this neighborhood here. Yeah, so that's formalized in this way. Yeah, so you update your new direction by taking the average over all neighbors, yeah, over all neighbors. But you also make a mistake. Now you can have some random, some fluctuating force that actually changes the direction you're pointing at. Yeah, so you're basically doing like this. Yeah, and this force is, as usual, yeah, so this is Gaussian, it's uncorrelated, and it has, yeah, it's uncorrelated in space and time, and it has a strength delta, which we know because with equilibrium has something to do with the temperature, you know, fluctuation, dissipation theory. So that's the system. And now the question is, can we come to consensus on where to go to dinner? Yeah. So this system here has a rotational symmetry. Yeah. In this model, there's nothing that tells you so we should go east or west or north or south. Yeah, in the first place. What we're now asking is, can this rotational symmetry be broken? Yeah, can we align these arrows all in the same direction when one direction becomes special? Or will we always have a case where when we average over all directions, yeah, we don't get a clear answer where to go for dinner? Yeah, and the answer to this, yeah, think about the last slide, will depend on the strength of the noise, yeah, or the temperature. Yeah, for this delta equals 0, we can expect there's no other thing, there's only interaction and nothing else that stops you from aligning. Yeah, these pointers align in same direction. Yeah, so that's something we can expect. So what happens if we turn on the noise? What if we turn on the noise? So first, this noise is Gaussian. Yeah, so this noise is Gaussian. And this lecture will be full of hand-waving arguments. So that's why I'm getting away with school mathematics. Yeah, so this lecture is Gaussian. Yeah, and if we look in a certain time interval and see how this angle will change of a certain particle, yeah, then this follows a diffusion equation. Del T theta is something like diffusion equation nabla squared theta. Why do we get the diffusion equation? It's just like the random walks, like the Brownian motion. There's nothing here in this model that is that is out of equilibrium. You're being pushed in random directions, yeah, and you try to align with your neighbors, and this just gives you a diffusion equation or heat equation. Yeah. So we have this heat equation, And this heat equation means that we transport information about our angle diffusively through the system. Basically with a random, like a random walk. So remember the first lecture. So we transport information diffusively, and this means we transport information very slowly. It's a very inefficient way of transporting information. And now we come up with the first line of arguments that is very powerful in statistical physics. I don't know if you do that in statistical physics lecture, but it's very intuitive. And this is called a scaling argument. So what we're interested in for the rest of this lecture is not exact solutions of equations. We are not interested in prefactors or in numbers. We're just interested in exponents. We're interested in how things change when we go to infinity. When, for example, time goes to infinity, how fast do we go to infinity? And this is described by exponents. And this diffusion equation also has exponents. So we remember the first lecture, Brownian motion. Then we know that the typical distance, let's call it r, that this information travels, if it's governed by the diffusion equation, scales like the square root of time. This is the first scaling argument in this lecture. Another way to see that, I know it's a little bit, it always sounds fishy if you hear that for the first time, but it's a very powerful argument because you don't have to do any calculations. On the left-hand side here, we have something like 1 over time. The first derivative with time, something like 1 over time. And this here on the right-hand side is something like 1 over distance squared. So left is time, right is distance squared. And this is how you can get this relationship R scales like square root of time. But of course, this is also a basic property of any diffusion process, now that the mean square, the standard deviation increases with the square root of time. So this is the first step. And now what is R and T? So I didn't tell you what R and T are. R and T are some, time, and length scales. Now, for example, this R is the distance or proportional to the distance or scales with the distance over which a perturbation delta theta spreads. It's a typical length scale of that. We can't give it a number or so, but we're not interested in the number. It's just the distance, and one example of such a typical distance is the length scale over which a perturbation spreads. We can also say if you have a multi-dimensional system, that's the volume. So we have a volume, and if the length scales with the square root of t, then the volume scales with time to the power of d over 2. So nothing really is happening here. You just have to digest that you can do these things and you can learn something. So that's the only tricky thing with these scaling arguments. At first they sound fishy, but if you see the end results, they make sense. And the reason is that we're not asking quantitative questions, we're asking questions of scaling behavior. How do things scale with in relation to each other? How do they change in relation to each other? But here this means length scales and time scales scale in this way because they're defined by a diffusion equation. That's how to read these things. And now we go on with school mathematics. Now let's go on with school mathematics. Yeah. Now we just plug things into each other. So we can calculate different things. So first, the error, wrong color. Error per pointer. Yeah. And that's what we call delta theta. And this scales like, now we leave away any prefactors or anything, delta theta I over the volume. Now we have to divide by volume, yeah, and then this goes with t to the minus t over 2. And now we can ask how many errors or how many of these fluctuations in the wrong direction do we have per volume? Yeah, number of perturbations in volume V. Yeah, we call that n. And this scales like the time to the power of the volume. Yeah, the volume tells you how many particles do I have, how many pointers do I have, and the time tells you how long you're looking. Yeah, it's a very trivial relationship. Yeah, and then we just plug this in, and we get t to the d over 2. Now, what is now the typical scale of a fluctuation? Yeah, we have central limit theory. We have many fluctuations, you know, summing over many fluctuations. We find that we have a typical size, you know, of these fluctuations that goes with the square root of n. Now that's just the central limit theorem. Yeah, there will be some prefactors, there will be all kinds of complicated things, but we know it will, because of the central limit theorem, scale with the square root of n. And this scales with, again, leaving away any prefactor, times time times volume. Yeah, this is the central limit theorem. And now we can look at a certain region in space and ask how is a single pointer affected by this fluctuation, by this omega. Now, density per pointer, that's the density. And then we take this capital omega and divide it by the volume. Yeah? And this goes like time over, if you just plug this in, time over volume, again, just plugging in, r to the power of minus 1 minus d over 2. Yeah? What does it mean now for large distances? Yeah? How does our, so we have, look, so we have a homogeneous system. We, you know, all are looking, suppose we are all looking in the same direction. Yeah, think about the Ising model in the first slide. All spins are pointing in the same direction. All people are looking, pointing in the same direction. Yeah, now somebody turns around and shows somewhere else. Yeah, so that's an error, or that's a that's one of these perturbations that we had on the first slide, where we introduced these wrong spins and saw whether they changed the free energy. Now here we do the same thing. We turn somebody around and ask whether this turning around of this person will destabilize the entire system. And it will destabilize the entire system if this information of somebody turning around propagates through the entire system. Yeah. And now we can see, so we are interested in this R to infinity. So this goes to 0 for d larger than 2. Yeah, this propagation, this error, this fluctuation decays with the distance. Yeah, it will at some point it will vanish. So in d larger than 2, we can have an order. Yeah, we can arrange in the same direction. This goes to infinity for d smaller than 2. Yeah, for d smaller than 2, this goes to infinity, and we cannot have any order. Yeah, because somebody turns around and it destabilizes the entire system. Yeah. So this error here will increase and become infinity. Will go into the entire system. And then for d equals 2, we actually have to do some mathematics. Then we see that this depends on the system size, but this also then goes to infinity. So what does this mean? What have we learned? So this was an equilibrium system. There was nothing that was out of equilibrium. And actually this system is more or less equivalent to the XY model. So we have spins at the plane, and they turn at an angle, and you see whether you have alignment. It's the XY model in statistical physics. And we've seen that for d larger than for the dimension larger than 2, we can have long range order because these fluctuations or these errors are introduced, they decay, they become small. For d equals 2 or smaller, these fluctuations or these perturbations, I perturb somewhere, I have a little noise, this will immediately spread and destabilize our order. Yeah? Any long-range order is destroyed for dimensions equal or smaller than 2. And that's actually here a manifestation of the Mermin-Wagner theorem from equilibrium statistical physics, which tells you that you have a system described by some Hamiltonian, and you have a continuous symmetry. That means that continuous symmetry means that unlike in the Ising model, where you can decide between +1 or -1, in a continuous symmetry, you can change your state continuously. That can take a real value, like in this case here, an angle. Yeah, so if you have a system and 2 or less dimensions that is in equilibrium and that has some short range interactions, then these symmetries cannot be broken. So that means that there cannot be any order. And the reason for this is, if you remember a statistical physics lecture, is that with very minimal energy cost, you can twist these directions very slightly and very slowly through the entire system. Yeah, and by this you can break, you can destroy any order with very minimal energy deconsumption. If neighboring spins or if neighboring pointers just differ by a small amount. Yeah, and this is called a Goldstone mode. That destroys the order in the system. But of course, in these systems, many other things can happen. Think about Kosten and Staulis. You can have topological order. You cannot have an average spin, but you can have structures of vortices and so on in these systems happening. But here in equilibrium, again, the message, if we ask how fluctuations, how an error progresses throughout the system, is it does it decay? Is it repressed? Or does it grow? That tells us something about whether or not long-range order can exist, yeah, whether all of these pointers can point in the same direction. Yeah, this is formalized in the Mermin-Gardner theory. And just to emphasize that this is the same idea that we had in the first slide here in the Peierls argument in the Ising system. We introduced a perturbation here. And then we didn't look at this dynamically, but statically. So we asked, is this perturbation actually favorable or not? If it's favorable, you have these perturbations all the time, and this perturbation will actually survive in the long term. It was the same reasoning, but because we are here in equilibrium, we can have a very elegant formulation with the free energy. And now with these pointers, yeah, so we could have, of course, made a similar easy argument, but we went to the dynamic direction to see how things spread over time and in space, because of course this is where we'll be heading now in the next step when we go to out of equilibrium. Okay, so how can we go out of equilibrium? Now, how can we not be in equilibrium here? The way we can do that is by making the particles move. Yeah, so, and remember, we had that in the very first lecture as well with these active Brownian particles, with this bacterium, and this bacterium was consuming energy, yeah, and it was turning this energy into kinetic energy. It was taking up chemical energy and was turn it into kinetic energy, and using this kinetic energy, it would so that propel flagella, that were pointing out of this bacteria, and that would make the bacterium move ballistically through the system. Yeah, but that was a single bacterium. Here we're now looking at how these bacteria behave. So say if you put many of them into the same system. And one of the first people who was looking at these kind of systems was called Thomas Wischek. And he defined a model with very few ingredients, actually. Yeah, so the first ingredient is that you have self-propulsion, that you have this bacteria, and this bacteria, they move, if nothing happens, they move ballistically and in the same direction. Yeah, and this already tells us that the system is out of equilibrium because you necessarily break the fluctuation dissipation. Then these particles interact, and they interact by following their neighbors. And that's exactly the same thing as with the pointers in the previous case. And these interactions are, as previously, short range. Which means that they have a limited distance over which they're interacting, typically called R0. You see it also in this picture on the top right here. So you have a circumference around the particle, and what you then do is you average your direction over all particles that are in your neighborhood. So now we also have errors. So we're not taking exactly the average direction, but the average direction plus some error that we make, plus some fluctuation, plus some fluctuating force that we can't predict. So then we have noise. And that means, as before, that we can formalize this, that as the next time step, you take the direction that is the average over all your neighbors. And then you have some noise, eta of t. Yeah. So, and then last, you again also have rotational symmetry. And this rotational symmetry again means that there's no a priori direction in which these particles move. So if nothing happens, if you didn't have any interactions, or if you on the microscopic level, if you pick a random particle, then you would expect it to move also in a random direction. And now we ask again, can this rotational symmetry be broken? So if you write down here some equations, there's nothing that points out a certain direction. There's no north or east in the equations or in the simulations. But can we have a preferred direction nevertheless on the macroscopic scale if we average over all particles? So this looks like very much like the system we had on the previous slides, the equilibrium system. The only difference is that these particles are moving. So what does it actually mean that they are moving? What is actually the essence of that? So if they were all moving together with each other, you could just go into a reference frame and then you would be back in the original system, in the equilibrium system. But what is happening here is not only that they're moving, but because they're moving, they're changing their neighbors all the time. So you remember in the previous case, we had you have your neighbors, and then you do something, you align, and then this alignment information or your angle information is transported diffusively to your over your neighbors, through the system. Now your neighbors change. And because your neighbors change all the time, also the information in which direction you're going is propagated in different ways. And that's actually all the magic. Now, as a first step, let me just show you that you can actually describe the system in the kind of equations that we were looking at in the previous slides, in the previous lectures. So this is the stochastic differential equation that describes the dynamics. And the way, so we won't go in, we won't use it here. I just wanted to point out that first, such an equation exists, and also the way you can derive it. So what you do is basically you go from particles to fields. That means you zoom out. You're only interested in resolving slow changes in the densities and direction. And that's always the assumption that you make if you go to a field. And in this, if you do that, then you just write down all possible terms that are in agreement with the basic symmetries of the microscopic rules that describe the dynamics on the previous slides. Then you get tons of different terms that are in agreement. And what you then do is that you reason which terms are actually important. And you can do then arguments from renormalization group theory, for example. Is a term actually important to understand these exponents or not? You can make other arguments. And this is how you derive these equations. Another way to derive these equations is by starting from a microscopic theory, by really with some Hamiltonian or so, some Boltzmann equation or so, and then derive in a very lengthy calculation, derive these equations that you see here. So this equation that you see here has a time derivative of the velocity. And then here is a convection term, things that flow in some direction, that's a flow here. And then here you have a potential for the velocity that looks like this. Is the typical potential that you assume here. There's no underlying microscopic reason for this necessarily. And this potential just says that the average velocity should go to some kind of minimum. So that these particles in the end all have some similar average velocity. That's what unit is for. You have a term that depends on the pressure. Now you want to punish particles all being on the same position. And then you have your terms that also come in, that also have some not so intuitive meanings. But if you are in have a background in hydrodynamics, for example, you see here a term that a prefix that describes a bulk viscosity, and this would be a shear viscosity. And this equation overall looks also like the Navier-Stokes equation. Yeah, so it looks a little bit like the Navier-Stokes equation. And then you have here the fluctuating force that is a Gaussian and uncorrelated. And you have an additional equation on the bottom that describes that the density can only change if you take particles from another part of the system, so that the mass of the system is actually conserved and these particles cannot disappear into nowhere. I just want to tell you that you could now take the tools that we derived in the last lectures and derive a field theory from that, or to derive to do renormalization on that, something that we'll do in December. And then you'll get to very similar results, and I'll show you now for the rest of the lecture. Now we won't do that here. So what we will do is we'll take the same sloppy but very powerful approach as in the beginning of this lecture. We look at scaling arguments. Before we do that, let's quickly have a look at such a simulation of such a system. Now we tune this noise parameter. Here's a 2D system, and we tune this noise parameter. On the left-hand side, if we have a very low value of this noise, you can see that these arrows all point more or less in the same direction. So we have polar order, or this rotational symmetry is broken. They're all going the same direction. If we have stronger noise on the right-hand side, then all particles are moving in different directions. Now they're moving in random directions. And if you average over these directions, then the average will be 0 if your system is large enough. So this looks like, so we just had the Mermin-Wagner theorem that tells us that in equilibrium systems, you cannot have such order. Now you cannot have alignment of these directions because perturbations, or if somebody makes an error, will grow and travel through the entire system and destabilize everything. Apparently, here in these kind of systems, you have a way of transporting the alignment information in different ways. And we now see how these particles manage to talk to each other over long distances through the entire system without this information about alignment being destroyed by noise. So to begin, let's look at the situation on the right-hand side. We look at, again, these perturbations in these angles. Think about the Peierls argument, for example. In the first slide, we perturb the system, and we look like how this perturbation travels through the system. Another way to look at this is to look at a domain of the reverse question is how actually not the perturbation, the error propagates, but how the alignment propagates. And this is described by these W's here, where we say, okay, so we have here the system, we have a particle that's moving in some direction. Suppose it's locally aligned. Suppose these particles are locally going in the same direction. Then this region here of correlates, this blob of particles that are going in the same direction, roughly the same direction, that has a size that is perpendicular to the direction of the center of mass here, and that has a size that is parallel to it. Now, unfortunately, I took a circle here, and I drew a circle, but of course, the point is that these directions can be different, and they will be different. So the alternative question is, how does the information about alignment propagate through the system? Okay, so let's first say, so suppose that there is a particle and now we have a perturbation. Yeah, somebody changes the angle. Because all of these particles are moving, if you change the angle, they will be moving into different directions. Yeah, and that means that they get separated over time, and the separation we can write down in these two directions, parallel and perpendicular to the direction of motion of the center of mass. Yeah, so the perpendicular direction is given by some velocity times time, and of course the angle, that's the sine of delta theta. Yeah, delta theta is the deviation in the angle. Now the parallel direction, just the geometric arguments, is 1 minus cosine of delta theta. This is the delta theta. Yeah, it's the cosine of delta theta. And now we can Taylor expand this. And then this will scale like t times delta theta. Taylor expand the cosine and sine. And the lowest order in the cosine is theta squared. Yeah. And now, so this is the first scaling relationship. And now we do the same thing as before. We plug these relationships into each other all the time until we have the exponent that we want to know. So next step would be to look at these W's here. So that means that we'll be looking at the propagation of information in a volume V that scales like, that is made of these omegas, these W's, the perpendicular direction to the power of d minus 1 dimension times the parallel direction. Right, so you have this red blob here, some typical size, and then if you make this a volume, then you have one parallel direction and d minus 1 perpendicular directions. Yeah, and now we look at how these W's scale. Now these W's scale with delta x perpendicular plus some number of spreading times the square root of t. Now then this number we just call d perpendicular. And I can imagine that many of you are now angry that you don't know what this d perpendicular is and so on. But that's not the point. Yeah, there's all these prefactors and so they're not interesting to us. It's just some number and we have to write it down because it's in this sum here. It's something. And then we just plug this in. That's t delta theta plus the perpendicular square root of tau. And now we define this as t to the gamma perpendicular. Now what just happened? We wrote down this stuff here. And we say that you have this delta theta here, you have this perpendicular, you have this one, you have all these components here. In the long times and over long distances, this has some effective exponent, gamma perpendicular. Yeah, this is the definition of this exponent. And that's what I use this sign for. Now let's look at W parallel. Yeah, this will be X parallel, the same thing, plus D parallel square root of T. Now this scales like T plugging just in plus D parallel square root of T. And I define that for long times and long distances. This goes with time to the power of gamma parallel. Again, gamma parallel is an exponent that we want to know. Yeah? So gamma parallel and gamma perpendicular are the exponents that describe how these W's on the left-hand side, behave over long times. Do they grow? Do they shrink? Are they diffusive or what? Yeah, so that's what's in these gammas here. And in the end, we will calculate these gammas here, and we will want to find an interpretation of them. Now let's call these equations 1 and 2. We'll use them later. And now we look at the density of fluctuations again. Now this delta theta. Yeah, and this, like last time, goes with time times volume over volume. Now that's what we use already in the pointer, whether with the static model or the equilibrium model. And this, I'll just plug in square root of time over square root of volume. And again, plugging in square root of time over, now plugging in the volume, omega perpendicular, d minus 1, omega parallel. And this we define to be our third exponent, t to the gamma. Yeah, this is our third equation. Now we have all these relationships here. Yeah, so for the gammas, connecting the gammas with something on the left-hand side. And again, these relationships here, these different exponents describe different things. Now the first two, the W's, they describe how order propagates, you know, how this blob, how this domain grows or shrinks. And what you can see already is that it will grow or shrink differently in the parallel and the perpendicular and in the parallel direction. Yeah, and this density of fluctuation here, fluctuations that describes, let's say, the opposite thing like the last time. How does an error, like a perturbation, a spin that you flip in some other direction, how does this propagate through the entire system? And now we do some algebra. Now we just plug these in to get the exponents. Yeah, we have three equations, three exponents. And what we now do is we say, okay, t to the power of 1 plus gamma plus d perpendicular times t to the power of 1 over 2 square root scales like t to the power of gamma perpendicular. Yeah, and from this we can already learn that for long times, this gamma perpendicular will either be given by the left-hand side, yeah, will either be given by this or by this, depending on what is larger. Yeah. So this is max of 1 plus gamma 1/2. And we can do the other thing. We can do the other thing. Also, here. Okay, so second equation, t to the power of 1 plus 2 gamma plus t parallel times t 1 over 2 is scales like t to the power of gamma parallel. And therefore, gamma parallel is whichever term on the left-hand side dominates for large values of t. So that means that this is the maximum of 1 plus 2 gamma and 1/2. And now we have our third equation. Our third equation is t to the power of 1/2 times, just plugging in, t to the power of minus gamma perpendicular d minus 1 over 2 t to the power of minus gamma parallel over 2, and this scales like t to the gamma. And therefore, we get that solving for gamma, 2 gamma is equal to 1 minus gamma perpendicular d minus 1 minus gamma parallel. Yeah, I mean, I just count the exponents. Yeah. Okay, now I counted the exponents, and now I can take these three equations here and solve them. We have three equations, three unknowns. I can just solve them, and I'll just tell you the results. Yeah, it's school mathematics. So that's 1/2 minus 4 times dimension, 1/2, 1/2. So in high dimensions, information about order, about interactions, or about alignment is transported in a very inefficient way, diffusively. This is this one here. And if we go to higher dimension, if we go to lower dimensions, then we have the case that you see here. That is another condition for where we solve these equations here. Now this gives us conditions that we have to distinguish. 7/3, smaller than d, smaller than 4. Then we get 3 minus 2d over 2d plus 1. Yeah, this will be 1/2. And this will be 5 over 2d plus 1. No, and this is the case that we have when we have. Okay, so what we see here already in this case is that now in the perpendicular direction here, in this perpendicular direction, this exponent is actually larger than 1/2. So that means we have super diffusion. Yeah, in other words, perpendicular to the average direction in the blob, perpendicular to that, information about alignment is transported very efficiently. Yeah, it's transported convectively. It's not diffusion. You don't have to talk to all of your neighbors and they go one by one, but it's like convectively. It flows through the system. Yeah. Super diffusive spread of orientation information. Yeah, and this is actually turns out to be a convective process. That this information flows and not just diffuses. Yeah, and then we have the last case. Yeah, d smaller. Sorry, it's already here. The last case is 1 minus d over d plus 3, 5 minus d over d plus 3, and 4 over d plus 3. Yeah. In this case, actually the alignment information is transported super diffusively, so very efficiently, both in the parallel direction to the flow and in the perpendicular direction. And in all of these cases here, this exponent is smaller than 0, as long as d is larger than 1 dimensions. And that means we can expect to have long range order. Yeah. And now I have to tell you something. I mean, these arguments here, I don't know if you find that easier than the plain mathematics we did in the last few lectures. Mathematically, they're much easier, but you have to swallow, so to say, the spirit of these arguments at some point. And this is very difficult to follow, I imagine, that you can come up with here these kind of things and do them one after each other, and it somehow works out. Every individual step seems a little bit fishy, but because you're only interested in exponents, now we're only interested in these gammas here, and only at very large times, for t to infinity. Only this is the reason why these arguments work so well, and only for these simulations that work, for these situations that work well. And we can actually do that and just neglect almost everything and just take the highest order contributions all the time. Okay, so now I have to tell you another thing. So you can do the same arguments rigorously mathematically using field theory, using renormalization. And then you'll actually find that the situation is more complex than I made you believe here. That the exponents are slightly different, and that in higher dimensions, that the difference between higher and lower dimensions is more subtle than I make you think here. But to get a qualitative idea of how order is established in these non-equilibrium systems, it works very nicely, and it is an analogy to the Ising system that I showed you in the beginning. You ask what happens to a perturbation, how does a perturbation like an error spread in the system, and how does a properly aligned domain spread in the system. Now, the information about alignment. This is what we've been looking here. And just to summarize, I think that the point that we get, so I told you there's no general theory about how order is established in non-equilibrium systems. But the point we get here is the following. Now, so there are two forces that determine whether you have order or not, and these are interactions and noise. And the balance between these two will decide how interaction information, how far interaction information can propagate through the system, and whether you're able to establish, to communicate between a large number of elements and make them align in the same direction. So what we need is that these perturbations or these fluctuations, these errors, that they should decay sufficiently fast, or vice versa, this information on alignment, this communicating your direction, should propagate fast enough or far enough. In equilibrium, we've seen that you have a fixed number of neighbors. And if you have that, then you share information in a very slow way, diffusively. And then in equilibrium, you're not able to arrange long range order because you can always destabilize it very easily. Out of equilibrium, our neighbors can change. Now we're not always surrounded by the same neighbors, but if we have a little angle to our neighbors, then this neighbor transports our alignment information to other parts of the system. And this is most prominent at the perpendicular direction to where we're going. Yeah, and this alignment information can not only flow diffusively, like in these equilibrium systems, but because we have now this non-equilibrium component, the active movement of these particles, it can be transported convectively. That means it can flow through the entire system like a transport process. Yeah, and with this, these non-equilibrium systems, order can emerge, although in similar systems you cannot have long-range order due to the Mermin-Wagner theory. Okay, great. So I hope we got a first idea. So because we don't have a rigorous theory of everything in non-equilibrium system, I think the important point is to get an intuition with simple arguments about how order can emerge and what are the components that are competing with each other that decide in the end whether you get order or not. And this idea that we had at the beginning about the Peierls argument is actually a very powerful idea that is very useful even when thinking about non-equilibrium systems. So with this, I'm done for today. Yeah, and see you all next time. So I think some of you might have some questions regarding the scaling argument. So if you have some questions, so what we can do is that I can send you some papers. I just send me an email and send you some papers or some text of where these arguments are done in detail, and so that you can get used to them and that you can see how they actually work really and why they work. Yeah, and the mathematics behind these arguments is actually, as you've seen, as school mathematics. Now, if you can have an exponent of something, you already know what you know enough mathematics for this lecture. Okay, thanks a lot. So I'll stay online in case there are questions, and I think there's at least one question by Matthew. And for the rest of you, see you all next week. Yeah, and sorry to those who I didn't reply to in the emails yet. So I had a very busy inbox.